Every year, over 1 billion square feet of laminate flooring are sold worldwide. We see this covering every day at home, in offices, and even in shopping malls. But few people realize the complex engineering hidden in each plank. Imagine, under a pressure of over 1,000 pounds and at a temperature higher than 400 degrees Fahrenheit, thin layers of paper and resin are transformed into an ultra-durable surface that challenges stone itself. The laminate market is valued at tens of billions of dollars, but behind these numbers is a process that is impressive in its scale and precision. Watch until the end, and you'll discover the secret that your floor is hiding. Laminate, which has become an extremely popular choice for flooring, combines aesthetics, durability, and cost-effectiveness. Its production begins with the careful selection of raw materials and ends with the creation of finished panels, ready for installation. For the manufacture of laminate, 4 main components are used: the substrate, a stabilizing layer, decorative paper, and a protective layer. Each of these elements plays a key role in the formation of the final product. The process begins with the preparation of the core, or the base of the laminate, which is the most important part that provides its strength and stability. This core is made from a high-density fiberboard, known as high-density fiberboard. The production of HDF begins with sawing wood, mainly coniferous species, into small chips. These chips then undergo a steaming and cleaning process to remove foreign impurities. After this, the wood is transformed into fibers using special mills. The resulting fibers are mixed with glue, most often based on synthetic resins, and formed into a thick, soft mat. Next, this mat undergoes hot pressing under a pressure of about 700 pounds per square inch, at a temperature of 400 degrees Fahrenheit. This pressing compacts the fibers, forcing out moisture and air, and creates a strong, uniform HDF board. The thickness of such boards is usually from 1/4 of an inch to 1/2 an inch, depending on the laminate class. The quality of the board directly affects the moisture resistance of the finished laminate, its bending strength, and overall durability. The next important stage is the preparation of the decorative and protective layers. The decorative layer is a special paper on which a printed pattern is applied, imitating wood, stone, or another material. This paper is impregnated with melamine resin, which, after polymerization, gives it hardness and wear resistance. The protective or overlay layer is also paper, but it is impregnated with an even greater amount of melamine resin and small particles of aluminum oxide. Aluminum oxide, which is a very hard material, gives the laminate its main property: resistance to abrasion and scratches. The thickness of the protective layer is only a few thousandths of an inch, but it performs a critical function. Both of these impregnated paper layers are dried and stored in rolls until the pressing moment. The third layer, the stabilizing or balancing layer, is placed on the lower side of the base. This layer also consists of paper, impregnated with resin, and serves to prevent the board from warping. Without this layer, during use, the difference in pressure and humidity between the upper and lower layers of the laminate could lead to the panel bending. The stabilizing layer helps to maintain the geometric stability of the board. The key moment in the production of laminate is the hot pressing process, which combines all 4 components into a single monolithic panel. This takes place on multi-layer presses, where the prepared sheets are assembled into a sandwich. First, the stabilizing layer, then the core. After that, the decorative layer, and on top, the protective overlay. This multi-layer structure is placed in a press, where under the influence of high temperature, which can reach 420 degrees Fahrenheit, and a pressure of 1,200 pounds per square inch, the melamine resins melt and harden, securely bonding all the layers together. This process takes from 30 to 40 seconds and is called lamination. During pressing, the surface texture is also formed, which can imitate the texture of wood. After pressing, the laminate sheets are cooled and stabilized, which is important to prevent deformation. When the panels have cooled, they are sent for trimming and milling. At this stage, the large sheets of laminate, which can be 8 feet by 4 feet in size, are cut into smaller, standard-sized panels. For example, 48 inches by 6 inches. After trimming, locking joints, known as a click system, are milled on the side edges of each panel. This is a key feature of modern laminate, which allows it to be laid without using glue. The milling process must be extremely precise to ensure a perfect connection between the panels. Tolerances are only a few thousandths of an inch. The final stages of production include quality control and packaging. Each batch of laminate is tested for abrasion resistance, impact resistance, moisture resistance, and other parameters. The abrasion resistance test, known as the Tabor test, determines the wear class of the laminate. A high class means that the laminate will withstand a greater number of abrasion cycles. After successfully passing all tests, the panels are sorted, packed in sturdy cardboard boxes, and prepared for shipment. The weight of one box can be 40 pounds. All these processes, from the transformation of wood into fibers to the packaging of finished panels, are part of a highly automated and technologically complex production cycle. The result is a laminate that not only has an attractive appearance, but also high performance characteristics, which makes it one of the most popular flooring options in the United States and around the world. The total length of a production line can reach hundreds of feet, and the production speed is measured in thousands of square feet per hour. Understanding these processes helps to appreciate the complexity and engineering excellence of the product that we see every day in homes, offices, and commercial spaces. The global laminate flooring market has shown stable growth in recent years, driven by its popularity as an affordable, durable, and aesthetically attractive covering. According to expert estimates, it is projected that by 2030, this figure will grow to $35 billion, demonstrating an average annual growth rate of about 4%. The main driving factors are the construction boom in developing countries and the growing popularity of do-it-yourself repairs in developed countries. The geography of production and consumption. The largest regions for laminate production and consumption are the Asia-Pacific region and North America. In the United States alone, the annual production of laminate reaches billions of square feet. Europe also remains a significant player in the market, but the growth rates there are somewhat slower. Approximately 40% of the global demand for laminate comes from the residential sector, while the remaining 60% is from the commercial and industrial sectors. A significant amount of wood raw material is used for the production of laminate. Typically, to produce 1 square foot of high-density laminate board, approximately 0.15 cubic feet of wood is required. Given the production volumes, this leads to significant consumption of forest resources, although most manufacturers use recycled wood or waste from the sawmill industry. Standard sizes of laminate planks in North America range from 48 to 60 inches in length and from 5 to 8 inches in width. The weight of one package can be from 35 to 45 pounds, depending on the thickness and density of the material. In the modern market, there is a growing demand for laminate with a high imitation of natural wood and stone. Over 70% of sales are for decors that imitate wood, with oak and maple shades being the most popular. The demand for water-resistant laminate is also growing, which occupies over 25% of the market and continues to increase its share, especially for use in kitchens and bathrooms. The next time you walk on your laminate floor, remember this epic story. So enjoy your renovated space. Imagine thousands of glass threads, thin as a hair, combined into a single river, are transformed into a material that is already challenging steel. This isn't science fiction, but modern production of fiberglass rebar. Every year, the world spends billions fighting rust, repairing bridges and parking garages destroyed by corrosion. But there is a solution, a composite that is twice as strong as steel, 4 times lighter, and doesn't even know what rust is. The market for this material is growing by 12% annually, and today you will see how a building material of the future is born from hundreds of bobbins and a barrel of resin. It all begins at one end of a huge workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall, several yards high, hundreds and sometimes thousands of huge bobbins are installed in neat rows. On each of them is wound the thinnest glass thread, or roving. This isn't the glass that windows are made of. This is a special fiberglass, which is produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. They will be our skeleton, our internal army, which will give the rod its insane strength. From each of these hundreds of bobbins stretches its own separate thread, and they all gather into one thick, fluffy bundle. It's like thousands of streams merging into one large river. This dry white bundle is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Each of the thousands of threads must be tensioned with the same force. If one thread sags and another is over-tensioned, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: baptism in resin. The dry glass bundle is slowly immersed in a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat, that will grow on the glass skeleton. This is a complex chemical cocktail. The base is usually polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will start a chemical reaction and force the liquid to turn into a solid plastic. Also, various additives can be added here. Pigments to give color, ultraviolet inhibitors so that the rebar is not afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to soak every, even the tiniest fiber. The bundle must be completely submerged in this resin so that not a single dry spot remains. The soaked, heavy from sticky resin bundle comes out of the bath and heads to the point of its birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round, polished hole, the diameter of which exactly corresponds to the diameter of the future rod. The die is heated to a certain temperature. When the wet bundle is drawn into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass together, forming a perfectly round rod. Third, the heat from the die starts the initial stage of the chemical reaction of hardening, or polymerization. The resin begins to turn from a liquid into a gel. At the exit of the die, we already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special bundle of the same fiberglass is wound onto it. A thin, resin-soaked thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled on the sticky surface, which sticks firmly to the resin. Now our rebar has not only strength, but also teeth with which it will hold onto concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization furnace. This is a long chamber that can stretch for tens of feet, inside which a high temperature is maintained, usually 400 Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively connect with each other, forming a strong, rigid, three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material, which firmly binds millions of glass fibers into a single monolith. It's like baking a pie. While the rod slowly moves through this hot tunnel, it acquires its final, stone-like hardness. But what pulls it through this whole long path, from the bobbins to the furnace? At the end of the line stands a special pulling device, which gave the whole process its name. Usually, these are two caterpillar mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads, and at a constant, precisely calibrated speed, pull it towards themselves. It is they who create the force that pulls the fiberglass through the resin bath, through the forming die, and through the furnace. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor appears an endless, perfectly even, hard and hot fiberglass rod. The final chord is cutting. Across the line is an automatic saw. It synchronizes with the speed of the rod's movement. At the right moment, makes a quick forward movement, and with a sharp whiz, cuts off a piece of standard length from the endless ribbon, for example, 20 or 40 feet. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And so, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and furnaces, have turned into a light but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungles. The fiberglass rebar market is not yet a giant like the steel market, but it is the coolest and most daring newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are simply insane. It is expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now about the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sounds boring? Now imagine it in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it is limited by weight. Or, for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can calmly carry whole coils or bundles of fiberglass rods, whereas a crane is needed to move steel. This is a colossal saving on logistics and labor. Second is strength, and here fiberglass simply enters the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing an ordinary rope with a climbing rope. At a smaller thickness, it withstands much greater loads. But the main trump card, the real superpower of fiberglass, is its war with rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. Rust increases in volume and literally tears the concrete from the inside. Annually, the United States spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass, it just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years, and a structure with fiberglass rebar is calmly designed for more than 100 years. Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground. That's so much steel that it would be enough to build several aircraft carriers. Imagine, these metal giants don't rise up into the sea, but disappear underground, holding our cities, dams, and ports from destruction. But how is a perfect steel profile, with a tolerance smaller than the thickness of a fingernail, born from a pile of old scrap? What happens in the furnaces with 3,000 degrees and on the rolling mills, where metal is formed at the speed of a car? Watch until the end, and you will discover the secrets of production that are usually hidden from prying eyes. Annually in the United States, hundreds of thousands of tons of these profiles are produced and driven into the ground. To imagine this weight, think of an aircraft carrier. One such ship weighs about 100,000 tons. This means that in a year, the country creates enough sheet piles to build several such steel floating cities. This is an endless stream of metal that goes underground to hold what is on the surface. It all begins, as in many stories about steel, at a huge scrap metal yard. This is a place where old ships, building structures, and industrial junk get a chance for a new, noble life. A giant crane with an electromagnet gathers tons of this metal and loads it into a huge ladle, which is sent to the melting shop. There, in the roaring hell of an electric arc furnace, where the temperature reaches 3,000 degrees Fahrenheit, this scrap is transformed into a boiling lake of liquid steel. Special alloying elements are added to this melt so that the future pile is not only strong, but also resistant to corrosion, as it will have to work for decades in moist soil. Next, this fiery river passes through a continuous casting machine, where it cools and solidifies, turning into a long, red-hot steel billet called a slab. This is our blank, our formless piece of dough, in which all future strength is already embedded. These hot slabs, cut into pieces of the required length, are sent to a reheating furnace. There, in a controlled heat, their temperature is again brought to the ideal plastic state, about 2,200 degrees Fahrenheit. They become soft and pliable, ready for the main transformation. And now the most interesting part begins: rolling. The red-hot slab comes out of the furnace and enters the rolling mill. It's necessary to form not just a symmetrical profile, but a complex shape with bends and, most importantly, with a perfect lock on the edges. The rolls of the rolling mill for sheet piles are not just cylinders. They are real sculptors of steel, having complex shaped grooves. The slab flies into the first pair of rolls with a roar, which squeezes it and begins to form the main profile, usually Z-shaped or U-shaped. Then it passes through the next pair, which further refines the shape. And so, step by step, passing through dozens of such rolls, our flat bar is transformed into a long, ribbed ribbon before our eyes. We talked about locks or interlocks. Well, the tolerance in their manufacture is only a few hundredths of an inch. That's less than the thickness of a fingernail. The red-hot steel ribbon flies along the rolling mill at the speed of a car, and at this moment, the rolls form a lock on it with such incredible precision. This is necessary because at the construction site, workers will have to connect hundreds of such piles. If the tolerance is even slightly larger, this giant industrial zipper simply won't close. On average, 1 square foot of a sheet pile wall weighs from 20 to 40 pounds. And now imagine one pile 60 feet long. Its weight can easily exceed 3,000 pounds. This is like the weight of a small sedan, concentrated in one long, thin piece of steel. And these piles, interlocked together, form a wall capable of withstanding the pressure of earth and water, equivalent to the weight of dozens of trucks pressing on it simultaneously. But the most important thing happens at the edges. The last sets of rolls, finishing rolls, form the most complex element of the pile, the lock or interlock. On one edge of the pile, a groove is formed, similar to clasped fingers, and on the other, a protrusion, similar to a thumb. These elements must be formed with an accuracy of a fraction of an inch. If the lock is too tight, it will be impossible to connect the piles at the construction site. If it is too loose, the wall will not be sealed and will leak water. Therefore, the rolls with incredible force, but at the same time with precision, press out this complex profile along the entire length of the red-hot steel ribbon, which can reach several hundred feet. The hot, perfectly formed pile crawls out of the last roll and along a roller conveyor goes to a cooling table. There, slowly cooling, it acquires its final strength. After cooling, it is checked for straightness and, if necessary, straightened on a special straightening machine. Then it's time for the final operations. A huge cold saw, with a deafening roar, cuts off piles of standard length from the long ribbon. Inspectors take special templates, or gauges, and carefully check the geometry of the locks. They check whether the fingers and groove fit perfectly, whether there are any defects that could prevent connection. This is a guarantee that, at the construction site, somewhere in a deep pit, these steel sheets will connect into a single, strong, and waterproof wall. Some piles may undergo additional processing. A special sealant is applied to their locks, which, when connected, fills microscopic gaps, making the wall completely sealed. The finished checked piles are collected into bundles, marked, and loaded onto railway platforms or barges by giant cranes. And so, these steel soldiers, born in fire and pressure, are ready to set off for their service, to go underground and silently, invisibly to all, bear the weight of the earth and the pressure of water, making the construction of the most daring modern projects possible. The lion's share of sheet piles is used in marine infrastructure, the construction of ports, piers, docks, and breakwaters. They are the silent guards of our coastlines. A huge number go to flood protection, forming the core of dams and levees along rivers, especially in places like New Orleans. And of course, they are indispensable in large cities, where a deep pit needs to be dug for the foundation of a skyscraper, right in the middle of dense development. This steel wall, driven into the ground, prevents neighboring buildings from sliding into the pit. So these hundreds of thousands of tons of steel are not just production statistics. They are a measure of our ability to tame the land and water, to build where it was previously impossible, and to protect our cities from the elements, one precise lock at a time. The finished piles lie in neat bundles, resembling giant packs of pencils. The first move is made by overhead cranes. A huge beam moves under the ceiling of the workshop. Powerful electromagnets or special traverses with several hooks hang from it. With a hum, the crane descends, and with a metallic clang, it picks up a whole bundle of piles, which can weigh 30 tons. The crane operator transports this cargo and carefully places it on a transport vehicle. And here we have two main paths, by land or by rail. If the construction site is relatively close, the piles will go by truck, but these are not ordinary semi-trucks. To transport 60-foot piles, special extendable platforms are needed. This is a very long trailer that can extend like a telescope, reaching an incredible length. Due to the length of the cargo, the driver needs incredible skill to navigate turns. Often, such cargoes are accompanied by special vehicles with flashing lights, which warn other drivers and help in difficult sections. Every turn at an intersection is a slow, calculated maneuver that requires all the available space. If the distance is long and the order volume is huge, the railway comes to the rescue. Bundles of piles are loaded onto long, flat car wagons. This is much more efficient for large batches. An entire freight train, loaded with hundreds of tons of steel piles, looks like the spine of some prehistoric beast. With a rhythmic clatter of wheels, it travels hundreds of miles, crossing states, to deliver its cargo to the station nearest the construction site. There, the piles are reloaded onto trucks for the final throw of a few miles. Every year, over 25 billion square feet of oriented strand board are produced worldwide. Imagine, this amount would be enough to cover the entire state of Delaware. Twice. Or to build a path around the Earth over 190 times. Plywood was once the king of the market, but the 80s changed everything. And today, OSB controls over 75% of American construction. But how is a material that changed the industry forever, born from young trees, through hot baths, giant graters, and infernal presses? Watch closely. At the end, you'll learn a secret that even builders keep quiet about. It all begins not in a waste warehouse, but in the forest. For the production of high-quality oriented strand board, preference is given not to random offcuts, but to whole logs, usually from relatively young, fast-growing trees like aspen or southern yellow pine. These forests are often managed and self-sustaining, which makes the process more environmentally friendly. When the logs, tens of feet long, arrive at the factory, they are not immediately sent to the workshop. First, a hot bath awaits them. They are immersed in long pools of hot water, or placed in chambers where they are treated with steam. This isn't just washing. This process, which lasts several hours, softens the wood, and most importantly, weakens the bond between the wood and the bark. After this sauna, the logs go to a debarking machine. Imagine a huge rotating drum with protrusions inside. The logs, rubbing against each other and against the walls of the drum, and the bark flies off them like a husk. Bark removal is a critically important step, as bark lacks strength and does not glue well, so it is an undesirable impurity in the final product. Annually, factories in North America produce over 25 billion square feet of oriented strand board. This number is so absurd that it's hard to comprehend. Let's try. If you took all this quantity of panels and laid them out, you could completely cover the entire territory of the state of Delaware. Twice. Or build a continuous 1-foot wide path that would wrap around the Earth at the equator over 190 times. This is not just a lot, it's total domination. For decades, plywood was the king of the market. But in the 80s and 90s, this daring newcomer came onto the scene. And today, oriented strand board controls over 75% of the sheathing market for walls and roofs in residential construction in the United States. This was a real quiet revolution. The cleaned, light, and still damp trunks are ready for the main event, transformation into thousands of thin ribbons. They go to a machine called a strander, or a flaker. This is the heart of the whole process. Imagine a giant metal disc rotating at a frantic speed, equipped with dozens of sharp, scalpel-like knives. The log is slowly fed to this disc, and it shaves off long, flat, chip-like ribbons, strands. This is not chaotic shavings. Each strand has parameters precisely set by engineers. The length can reach 6 inches, the width, about an inch, and the thickness, only a few hundredths of an inch. It is this geometry, this noodle shape, that is the key to the future strength of the oriented strand board panel. When ordinary boards are made from a log, a significant part of it, up to 50%, turns into sawdust, offcuts, and shavings. And in the production of oriented strand board, from 85 to 95% of the entire wood of the log is used. We will talk about this later, but practically nothing goes to waste. The strands are cut from the entire length, and the bark, sawdust, and the smallest particles are burned in furnaces to provide energy for the factory itself. This makes this material not only cheaper, but also much more environmentally responsible. The resulting mass of wet, fresh chips, resembling a huge pile of light noodles, is stored in special bunkers, and from there, it is sent for drying. This is a huge, multi-story drum, slowly rotating, half a football field long. Inside it, a high temperature is maintained, and while the strands are slowly tumbling, moving from one end to the other, a stream of hot air evaporates the excess moisture from them. The moisture needs to be reduced from 50 or 70% to only 2 or 3%. This is absolutely necessary so that the resin can properly soak the wood and glue it firmly. After drying, the strands pass through a system of huge vibrating screens, which sift out particles that are too small, for example dust, which will go to fuel for the same dryer, and pieces that are too large, which will be sent for regrinding. Now the perfectly dry and sorted strands are ready for impregnation. They enter a huge, slowly rotating drum mixer. While they are being mixed, a sticky chemical cocktail is sprayed onto them through special nozzles. The main ingredient is a waterproof resin, which will be our glue. The second important component is paraffin wax. It envelops each chip like an invisible raincoat, and it is this that will give the future-oriented strand board panel its famous moisture resistance. And now, the smartest and most important part of the process begins, which gave the material its name, orientation. The strands, impregnated with glue and wax, go to a long, wide-forming conveyor. Here, a whole system of mechanical choreographers works. Special discs, rollers, and combs that lay out the chips in a precisely defined order. First, the bottom layer is formed. The choreographers lay out the strands so that they all lie parallel to the long edge of the future panel, that is, lengthwise. Then comes the turn of the middle layer. Here the strands are laid out perpendicularly, that is, crosswise. And finally, the top layer is again laid out lengthwise. As a result, we get a thick, fluffy, 3-layer pie, where the fibers in each layer are perpendicular to the fibers in the adjacent one. It is this cross structure, which imitates the strength of plywood, that is the secret that makes oriented strand board incredibly strong in bending and resistant to deformation. This fluffy mat, which can be several feet thick, slowly moves to the final test, the hot press. This is a real industrial leviathan, a multi-story structure that creates colossal pressure and heat. The mat enters inside, and massive steel plates begin to compress it with a force of hundreds of pounds per square inch. At the same time, the press is heated to a temperature of 400 degrees Fahrenheit. This heat activates the resin, causing it to polymerize and permanently glue all the chips into a single monolithic shield. The wax also melts, even better impregnating the wood and filling microscopic voids. In a few minutes, the loose mass turns into a hard, incredibly dense, and hot panel. A huge master sheet comes out of the press, which can be 50 feet long and 12 feet wide. While it is still warm, its edges are trimmed with diamond saws, and then giant saws cut it into standard building formats, most often 4 by 8 feet. Markings with information about its thickness, class, and compliance with building codes are applied to the surface of the panel. Sometimes special tongues and grooves are cut into the edges so that the sheets fit together perfectly when installing a floor or roof. The finished, perfectly rectangular sheets are stacked in high piles by robotic manipulators, wrapped in protective film, and sent to the warehouse. And so, having passed the path from a whole log through a giant grater, a sticky shower, and the fiery embrace of a press, this honest, unpretentious, and insanely strong material is born, ready to become the silent but reliable foundation for thousands of homes across the country. For the construction of an average single-family home with an area of 2,400 square feet, approximately 8,000 square feet of oriented strand board panels are needed. This material goes into everything. They sheathe the exterior walls, creating a strong and rigid frame. They make a solid sheathing on the roof, on which shingles are then laid. And of course, they make the subfloor, which is the foundation for all rooms. In essence, the entire modern American house is a wooden frame wrapped in a strong cocoon of oriented strand board. Every year, over 500 species of bamboo are grown worldwide, and China holds the richest treasure of them all. Imagine this: 16 million acres of lush green forests, an area larger than all of West Virginia, pulsing with life and growing so fast you can literally watch it with your own eyes. Some species can shoot up more than a meter in a single day. This is where a $27 billion industry begins, an industry that feeds, clothes, and even builds entire cities. But behind this green marvel are secrets you've likely never seen. Watch closely. If you stay with this video until the end, you'll discover something that will make you see this simple grass in a completely new light. China is the undisputed king of the bamboo world. The country is home to over 500 bamboo species, and its bamboo forests cover more than 16 million acres. That's more land than all of West Virginia, covered entirely in a sea of green. This massive natural resource is the foundation of a multi-billion-dollar industry. China produces 80% of all bamboo products in the world, exporting them to more than 100 countries. It all starts not in a noisy factory, but in the silence and greenery of endless bamboo forests stretching across southern China. Standing in the middle of one, you're surrounded by thousands of smooth, perfectly straight trunks, reaching more than 100 feet into the sky. Sunlight barely filters through the thick leaves, casting a mystical green glow. And the only sounds are the soft whispers of wind and the gentle creaking of stalks brushing against each other. But bamboo's real superpower is its outrageous, almost indecent speed of growth. It's the rocket engine of the plant world. Some species, like the giant moso bamboo, can grow 3 feet in a single day. Imagine that. You could literally sit and watch it grow. In just a few months, a young shoot reaches full height. It's not a tree that takes decades. It's a giant grass ready for harvest in just 3 to 5 years. And here's the best part. When you cut one stalk, the root system stays alive and immediately sends up new shoots. This isn't deforestation. It's more like mowing a lawn, an endless, self-renewing resource. When harvest time comes, workers enter the forest. There are no roaring chainsaws or heavy machines tearing up the ground. Most of the bamboo is cut by hand, using simple saws or machetes. With a dry crack, the stalk falls to the ground. The branches and leaves are trimmed off, and the smooth, hollow green stems, called culms, are tied into bundles and carried out of the forest. This is the raw material, the uncut gem that's headed to the factory to be transformed into 1,000 different things. Bamboo is a true superhero in the fight against climate change. It absorbs carbon dioxide 35% more efficiently than most trees and produces 35% more oxygen. These 16 million acres of bamboo in China are giant green lungs working to clean the atmosphere. It doesn't need pesticides or fertilizers, making it one of the cleanest crops to grow. And unlike cotton, one of the thirstiest plants in agriculture, bamboo thrives on rainwater alone. Let's look at 2 of the most fascinating transformations. First, how do you turn a round, hollow stalk into a hard, flat floorboard, tougher than oak? The bamboo trunks are first cut into sections and fed into a machine that splits them into long, narrow strips, like a giant apple slicer. These strips still have a curved shape and outer skin, so they go through another machine that shaves off the outside and inside, turning them into perfectly rectangular slats. Next comes a spa treatment. The slats are boiled in hot water or steamed, not for cleanliness, but to remove all the sugars and starches that bugs and mold love to feed on. After that, the sugar-free slats are placed in a drying kiln, where they're slowly and carefully dried to a precise moisture level. Now we have thousands of perfectly dry, sturdy slats. Time to put them together. The slats are coated with glue and stacked into a mold, where a massive hydraulic press comes down. With a force of thousands of pounds per square inch and high heat, it compresses the slats into a solid, monolithic block. From this block, manufacturers cut floorboards, countertops, plywood, and even structural beams. The second transformation is even more astonishing. How to turn this tree-like grass into soft, silky fabric for a shirt or bed sheets. This is industrial alchemy. The bamboo culms are first chipped into small flakes. Then, the flakes are soaked in a chemical solution, usually caustic soda, that breaks down the cellulose, the plant's rigid framework. After several hours of cooking, the hard chips become a soft, thick mass that looks like paper pulp. This pulp is washed, bleached, and pressed to squeeze out excess moisture. What's left is a sticky, dense gel. This gel is then forced through microscopic holes in a metal plate called a spinneret, like a giant molecular meat grinder. On the other side emerge ultra-fine, continuous threads. These threads drop into a bath of another chemical, usually sulfuric acid, which instantly solidifies them. Now we have silky, shiny fiber, bamboo viscose. It's washed, dried, and spun into yarn, which is then woven into incredibly soft, breathable, and hypoallergenic fabric. Now let's peek into the world of small eco-heroes, the birth of a bamboo toothbrush. It all starts with harvesting mature 4-year-old moso bamboo. The trunks are cut, then sawed into long, even sections. These sections are split into thin slats. Next, the slats are run through a special milling machine. Imagine a high-precision pencil sharpener. It shaves the slat into a perfectly smooth, rounded stick, the future handle. This process is incredibly fast, with thousands of handles flying out every hour. Then comes heat treatment. They're baked to make them more water-resistant and to give them a beautiful caramel tone. Next step, the haircut. A machine drills dozens of tiny holes into each handle with surgical precision. Then comes the most fascinating part, bristle implantation. A machine, similar to a high-speed sewing machine, grabs a bunch of nylon or biodegradable bristles, folds it in half, and punches it into each hole using a tiny metal staple like an anchor. This happens dozens of times in seconds. The final touch, trimming. All the bristles pass through a trimmer to make them perfectly even or shaped. And that's it. Simple, brilliant, and much kinder to our planet. But these are just 3 examples. This green dragon has 1,000 faces. Young bamboo shoots are a delicacy in Asian cuisine. It's used to make billions of chopsticks, cutting boards, dishes. It's burned to create activated charcoal for filters. It becomes paper, blinds, furniture, even computer mouse shells. In construction across Asia, it's still used as incredibly strong yet lightweight scaffolding for skyscrapers. And this entire ecosystem, from the farmer cutting stalks to high-tech fabric factories, creates a $27 billion economic phenomenon. But what does that mean? That's more than the GDP of some small countries, like Iceland or Jamaica, and the number keeps growing. Just 10 years ago, the industry was half the size. Projections suggest that by the end of this decade, the global bamboo market could exceed $100 billion. and China plans to stay its dominant player. This isn't just about a few big factories. It's an ecosystem that supports over 35 million people, from rural farmers to designers in Shanghai. It's a story of how nature's wisdom, multiplied by human ingenuity, can turn ordinary grass into an infinite resource that dresses us, feeds us, and builds our world.